Good afternoon, yeah. And I'm really glad to be here, so thanks to everyone who contributed to that. This is joint work with Rupert Klein and Matthias Weidmann in Berlin, and also follow up on a lot of work we did with Marie and Kai. And I'm going to talk about the non-stationary boundary layer detachment and what the relationship with the energy dissipation. So there is a little experiment I like to do, which is just fill a glass of water. Of course, you can do it with any other liquid if you prefer. And what will happen is the water will come to rest, although if you look at the viscous timescale, it's horrendously long, and the Reynolds number, you can compute it, it's between 10 to the 4th and to the 5th. So what process allows the water to come to rest in a few seconds? Does anyone have a guess? Turbulence? But what is turbulence? Yeah. No cheating. So, I just want to talk about a very small aspect here, which has to do with the boundary layers. So first, I will explain the vanishing viscosity limit problem, and then do some explanations about the Prandtl theory, and then present some numerical results about Prandtl and Navier-Stokes equations. So if we want to dissipate energy, there's basically in incompressible flows, there's basically only one way to do that, is to create entropy. Okay, so we need to have high enough entropy, and in fact, as you see from this very simple equation, we need the entropy to scale like nu to the -1. Okay, so that this goes to a finite limit, which is independent of nu, and we can dissipate energy efficiently. And you know experimentally that flows seem to be extremely good at doing that for many reasons, as is shown by this just wake behind the sphere experiment. And there are basically two, you can think of two ways of doing this intuitively as a very first step. Either you have omega, which is scaling like 1 over square root of nu on a finite area, nu independent area. Or you can also have omega proportional to nu to the -1 over an area of order nu. That's another possibility. Okay, so please keep that in mind. And we know that turbulence has something to do with amplification of entropy, but I'm not going to talk about that at all here. So I'm taking a very limited view and just try to understand how can vorticity be created in the first place. And for this problem, it's actually already a very good thing to limit once to 2D, because of course for amplification we would need vortex stretching, which is only in 3D, but for creation of vorticity we can work with 2D. And as you know, vorticity is created at boundaries in reaction to pressure gradient. And we have this equation, which tells us that the inward, the flux of vorticity at the boundary is related to the tangential pressure gradient of the boundary. So that's good, but the problem is when nu goes to 0, can we get the sufficient vorticity to have the dissipative scaling that I showed earlier? And also how to compute this pressure field here. In fact, you can make a very quick computation from the Navier-Stokes equations, and you see that the pressure field also depends on the tangential gradient of vorticity at the boundary. So this is in fact a nonlinear boundary condition for the vorticity field. So to find the scaling when nu goes to 0, the simplest, or let's say the most natural approach is to do a boundary layer theory. And this was first proposed in 1904 by Prandtl. You can limit to to a very simple domain, so a half plane. And if you look at the vorticity, you assume the following ansatz, that the vorticity field can be decomposed into a new independent part, Reynolds independent, and then a boundary layer of width thickness scaling like 1 over Reynolds to the -1/2, or equivalently nu to square root of nu, sorry. And the amplitude of vorticity in this boundary layer scales like Reynolds to 1/2. And then there is a kind of error remainder term here. And if you plug this into the Navier-Stokes equations and turn the crank, do the right, keep the right terms, you will see that omega 0 has to satisfy the Euler equations, and that this omega 1, this boundary layer, has to satisfy this set of equations, which is the vorticity formulation for the Prandtl equations. It's not so natural to use the vorticity formulation for the, not so usual, sorry, to use the vorticity formulation for the Prandtl equations, but in fact, I find it very instructive because you really see here that the only influence of the external flow on the boundary layer is through this tangential pressure gradient at the boundary imposed by the external flow, as you see here. And the boundary condition at infinity is just omega 1 equal to 0. Decay quickly to 0. Okay? And we are going to simulate this set of equations. But first, we can already see that this is not going to give us the answer we're looking for, because if you apply the Biot-Savart kernel to this equation, given the scaling of the thickness of the boundary layer and of the amplitude, it turns out that the velocity, the far field velocity, which is generated by this boundary layer, will always scale like Reynolds to the -1/2. So we'll go to 0 with Reynolds, of course. And also the energy dissipation associated to this boundary layer will go to 0 like Reynolds to the -1/2. So you cannot dissipate a finite amount of energy when nu goes to 0 with the Prandtl boundary layer. Okay. And also you cannot inject vorticity into the bulk because everything keeps confined to the boundary layer. Of course, if you have boundary layer detachment, that's a different question, but then this ansatz is not the right one anymore. And so the entropy production we are looking for to explain the finite dissipation requires that somehow this Prandtl ansatz break down at some point. Okay, so the question is, how does this happen? And I'm going to present a few numerical simulations on this, but first we can refer to mathematics to tell us what are the constraints, what is possible. And there is this very important Cato theorem, which tells us that it's valid also in 3D, but let's just consider the 2D case. We have equivalence between these two conditions, that the viscous flow converges to a solution of the Euler equation uniformly in time on some finite time interval, okay? And that the energy dissipation rate inside a boundary layer, okay, that's just integrating the dissipation rate on this very thin boundary layer along the boundary, which has thickness scaling like nu. Remember, the Prandtl layer has thickness scaling like square root of nu. So this is much thinner. If this dissipation goes to 0, then we have convergence to the Euler solution. So if we want to break down this convergence, we have somehow to dissipate energy in this very thin boundary layer. Okay. And to study that numerically, I'm going to take let's move directly to the picture. So this is the results we had previously. We take, maybe I skip this and I go to the explanation of the geometry. It will be more easy to understand. So I take a 2D channel flow with the no-slip boundary conditions at the top and at the bottom, and periodic boundary conditions on the sides here. And I take this initial condition. So it's kind of a quadruple of vorticity. So this dipole will shoot to this boundary, this dipole will shoot to this boundary, and I'm going to concentrate on this lower boundary and see what happens there. So I want to compare three things: the Euler solution of the Euler equations, solution of the Navier-Stokes equations with some small viscosity, and solution of the Prandtl equations for this same problem. To approximate the Euler solution, there is a very simple technique, which is to use the symmetry. So I put the mirror image of the vortex on the other side, and then I integrate this without, I don't need any boundary condition here. It's just automatically imposed by the symmetry. And let's just show quickly the movie. Then what happens is that the dipole here pairs with this mirror image. There is no boundary layer, of course, here, and it just goes on and slides, continues to slide along the boundary. Okay, but of course that's not what happens in a viscous flow if I have a boundary condition along this line. For the Prandtl solver, I skip the numerical technicalities, and I will show you the movie. So that's the kind of solution we can solve in the boundary layer. So the vortex is coming from here. I have a pressure gradient on this boundary, and this is the vorticity which is generated in the boundary layer. And we can see already on this movie that something funny is happening for some time here. And I will explain in 1 minute what it is. And then for the Navier-Stokes solver, I'm going to use two different solvers. One is using a volume penalization method, which has a very good resolution far from the boundary because it's a spectral solver. But it doesn't match the boundary condition exactly. And then, so that's the volume penalization method. I just have my solution here, and the boundary is approximated by treating this region as a porous medium with very small porosity. And then the other solver is the second order finite volumes in space. And this is the solver of Matthias Weidmann. And it has the exact matching of the boundary condition, but it's only second order. It's not spectral. Okay? So this is the comparison of the solution with the two solvers. Sorry. So we see in both cases we have a very extreme vorticity which is created at the boundary here. Notice the color palette is only going to 1 in the beginning, and then the vorticity is multiplied by 15 or so. And we have some discrepancy between the two methods when the vorticity becomes very large. Here we have, it goes up to 20, here only to 15, because the penalization method has trouble matching the vorticity maximum at the boundary. But otherwise, other than that, the solutions are very close to each other. Okay? So we want to analyze that a little bit more quantitatively. First, what happens in the Prandtl solution? We know, this is already known, that there is a finite time singularity in the Prandtl solution. The numerical paper on this is 1980, Van Dublin and Chen. And what happens is that the gradient of vorticity blows up. The wall normal velocity in the boundary layer blows up, but the vorticity remains bounded. Okay? And that's very well reproduced by our solver. So if we plot the vorticity, so this is just the L infinity norm of vorticity with respect to time, as a function of resolution, it just remains bounded by this maximum value here. But if we plot the gradient of vorticity, it blows up very rapidly at some time, which we can estimate 55.8. And we can do some logarithmic plot to show that it's close to T0 minus T to the minus 2 singularity. Okay, so but what happens in the Navier-Stokes equation? Because of course they remain, the solution doesn't have a singularity. So we can zoom on the boundary to see how the viscosity regularizes the flow. So now this is the Navier-Stokes solution, but zoomed in the same geometry as I was showing the Prandtl solution earlier. So it's not, I don't do anymore the boundary layer approximation, but I still plot the boundary layer. Okay? And this is for the volume penalization solver. What we see is that, and you can check that quantitatively, that in the beginning, the solution is extremely close to the Prandtl solution. So I do have the expected asymptotic convergence. But as we approach to this 55.8 singularity time, you see what happens here. This vorticity has become very large here, but this is still very close to the Prandtl solution. So this vorticity here still scales like Reynolds to the 1/2 if you want. But here the gradient, the parallel gradient of vorticity is building up and becoming very large, which will lead eventually to the singularity in the Prandtl equation. And Navier-Stokes equation, what happens instead of this singularity is that there is a very strong new vorticity extremum, but of the opposite sign, which is formed exactly at the point where the gradient blows up in the Prandtl equation. And that's basically the new thing, which is, I think, is not really observed in other previous studies. And as I will show, this new maximum now scales like Reynolds to the 1 and not Reynolds to the 1/2. And then it leads to detachment. Okay. Yeah. Très bien. Merci. So let's plot the maximum with respect to time. So that's just the maximum of vorticity with respect to time. So we see that that's for the volume penalization scheme. We see that for the volume penalization scheme, we have a lot of trouble matching the vorticity maximum, because so this is for increasing Reynolds number, and this is the Prandtl asymptotic solution, which should be matched by this Reynolds number here. So we have a factor like 20 or 30% below due to the numerics, because the vorticity is smoothed at the boundary by the volume penalization, so we don't really catch this extreme maximum. But what is important is we see that going from this Reynolds to this Reynolds, we have a very extreme effect, and this is what I was showing on the movie, that this, the maximum suddenly rises to a much higher value. And this is even more, even clearer on the other numerical scheme, the volume penalization scheme, which has the exact boundary condition. Here we clearly see that we go much above the Prandtl scaling, which was here for the highest Reynolds number. And if we plot the maximum value attained by vorticity as a function of Reynolds, so that's now Reynolds number, maximum vorticity, we see that there is kind of a transition, and this is the Reynolds to the power 1 scaling. So for low Reynolds, we do have the Reynolds to 1/2 sort of scaling, which is consistent with the Prandtl theory. But for higher Reynolds, we see that we start to transition to a much stronger scaling. And if you remember, this is exactly the scaling we need to have finite energy dissipation. But if we look at the entropy, the problem is that if we look at the entropy, the things numerically are much less obvious. Let me show directly the second scheme. So that's the entropy now. The black curve here is the Prandtl scaling. And we see that for the highest Reynolds number, we do go a little bit above the Prandtl scaling. This is in logarithmic coordinates, but it's hard up to now, so we would need higher resolutions to go to higher Reynolds numbers to really see clearly the new scaling of the entropy. But it's very clear on the maximum of vorticity. Okay, so let me just wrap up what I said. So for unstationary boundary layer detachment at very small viscosity, one of the essential features is this, the production of dissipative structures by the wall. So this is allowed by having extreme vorticity values at the boundary, which then detach and move into the bulk, and then they can live their life and be advected, but they keep dissipating energy. And I've not had time to really extend on that, but for t lower or equal to the detachment time, the solution converges actually uniformly in time in the energy norm to the Euler solution. But for t strictly greater than that, according to the Cato theorem, since we are dissipating energy, we do not converge anymore to the inviscid solution. Remember, there was the equivalence between the two. And also very important, the detachment process involves spatial and temporal scales, which go down to Reynolds to the -1 at least. So if we want to develop, of course, the idea now would be to develop a new asymptotic theory for unstationary detachment by rescaling also time and scale at the detachment point. We would need to take into account these small scales. So this is not like triple deck or such theories which actually add the boundary layers above the other one. And it seems also that the Stokes pressure, so this nonlinear boundary condition on the vorticity, I think, plays a really key role on the detachment. And with that, thanks for your attention.
Thank you very much, Romain Nguyen-van-yen. Not Rick Klein, I'm sorry about that.
That's okay.
We got time for a question from somebody in the room.
In the case of Prandtl boundary layer, is there a mathematical proof for singularity formation?
In some cases, yeah, there is. So I put some many references at the end of the PDF file. And this reference here, Gérard Varret-Dormy, prove ill-posedness actually on some initial data. And I think there was also a proof of finite singularity, but I'm not sure which one. Which paper it was, but yes, this has been.
What is the essential feature which is lacking in Prandtl and which exists in Navier-Stokes?
It's the wall normal, wall tangential dissipation. Because in Prandtl, when you do the scaling, the term dxx of omega disappears. Whereas in Navier-Stokes, it stays there.
That causes a big change.
Yeah, that's why it can go singular.
Boundary condition.
Thank you. And a final question, please, from Steve Cowley.
I have two questions I'm going to cheat.
Final two questions.
Brinkman and Walker back in 2000 found that in certain circumstances the Prandtl equations didn't converge, the Navier-Stokes didn't converge to the Prandtl because of the onset of a short scale instability in something pretty similar to what you've done.
Okay.
You don't see it, so question one is, do you see any evidence of that? And the second question is, people have looked at the evolution of once the singularity started, because you can write down interactive equations. I can't remember what's happening near the wall, but you can generate higher shears there. Have you seen any evidence? How does that compare with what you're seeing?
So concerning the the first question, yes, I think it's the important is the scaling. So I haven't seen before this scaling like Reynolds to -1 for the time scale for the singularity. So that's what I think is new. But otherwise, it's basically the same. So there is a fast time scale instability, I think, due to this interaction with the Stokes pressure at the boundary during the blow up in the Prandtl equation. That's what I would get from that. And what was the other question?
Have you seen any evidence of the instability that Brinkman and Walker saw?
Well, this I don't know. I'm not sure. I would have to really. look at the paper again. I'm not sure. I cannot answer, sorry.
Okay, thank you very much again.